Okay, kids, we're back today with a lesson with me talking and showing you some stuff. Now, listen, I hope you were following the instructions because the first thing you should have done is watch the video that I found for you. It'll make this so much easier to understand. So if you haven't watched the video that I found for you, the link is in today's announcements. Do that first. Make it better for you. So, what are we talking about here? Light colors and the wave model of light. We covered how yesterday how light can have properties that make it look like a wave. We looked at a simulation of that. Now, if we were in class, we would actually be doing this. We would have something called a prism, and a prism is a transparent glass or plastic object with flat polished sides. In this case, it's a three-sided prism. And we would get a light source in class on our benches, and we would shine white light through the prism and then onto a piece of paper, which would act as our screen. We would have the white light dividing into the parts that make up the white light, the visible spectrum, which we looked at yesterday. Red, orange, yellow, green, blue, and violet. Now, some people like to sneak another color in there between blue and violet called indigo. That's okay. It's all just different people looking at things differently. So a prism, there it is, transparent glass or plastic object with flat polished sides. The light separates, right? The light separates into the colors of the rainbow. And I listed those colors before. And the range of different colors is called the visible light spectrum. Now, if we make a connection between what we're learning today and what we learned yesterday, we see that all the different colors of light, because remember, we're looking at light as a wave, all the different colors of light have a different frequency. Frequency is a concept we covered yesterday. So there's the numbers. They all have a different kind of frequency, and they all have a different wavelength. And wavelengths are usually measured in nanometers. Nanometer being times 10 to the negative 9 meters, very small. And these frequencies are huge. So color of light is directly related to the frequency and the wavelength of the light. Now, what we want to do now is take a look at what happens when you mix different colors of light. So instead of starting with white light, we're going to start with different colors of light and see what happens when we mix together. Where would something like this occur? Well, something like this might occur in theater arts in a play where they're shining different light on actors. It happens with your computer screen that you're looking at right now to create all these different colors. And this is known as the additive color theory of light when you're adding together different lights. So three different light bulbs, for example, of different colors. We would have done this exact uh, lab in class, but we're not there. I'm sorry about that. I would have had a red light bulb. I would have had a green light bulb. I would have had a blue light bulb, and I would have showed you what happens when they mix, but we'll do the best we can. So the additive color theory of light states that white light, and I'm emphasizing the word light here, we are not mixing paints and pigments like in art class. We're mixing light, is composed of different colors, wavelengths of light. It is possible to produce white light by combining only three colors. So you don't need the full rainbow to get back to creating white light. One such combination is red, green, and blue. These three colors of light are known as primary colors. If you mix correct amounts of all three primary colors of light, you will make white light. If you mix only two of the primary colors together, you will make a secondary color. The secondary colors for red, green, and blue are known as magenta, yellow, and cyan. So here's a picture, and we would have done this in class. I would have had a red light bulb, a green light bulb, a blue light bulb, and when I would have shone it onto a piece of white paper. And where all three colors are together, it would have looked white. We would have created white light. Where red light and magenta are shining together, it creates magenta light. Where red light and green lights are shining together, it creates yellow light. And where blue light and green light are shining together, it creates cyan. So here they are. These are known as the secondary colors. We have magenta, kind of purpley, yellow, well, kind of yellowy, and cyan, kind of blue, green. So here we are with a little simulation, and I put a link to this simulation. You can play with it. The most red that you can get when following the additive color theory is 255 units of red. That's as red as it gets. I can scale it back down and it doesn't get as bright. There's still some red there, but not as bright until you get to 0 when there's no red light there at all. So it goes from 0 to 255. Green also, as green as you can possibly get, is 255 units of green. And I can make it not as bright or no green at all. And the same thing for blue. So instead of going from 0 to 100, it goes from 0 to 255. If you're a computer programmer, you would know about this unit of 255 maxing out. And as I showed you, you can mix different colors together. In this case, red and green. But I can change the amount of green that I get in there. And look, I get a variety of colors. I can change the amount of red I get in there. And look, the color here in the middle, which is usually yellow, you get different shades of yellow. Or I can change both, right? And when I change both, everything becomes darker if they equal each other out. So this is how computers make a variety, and TV screens make a variety of different colors. We do the same thing here, right? Blue and green, change the amount of green, you get a different mixture. Change the amount of blue, you get a different mixture. And right here with red and blue, which produces magenta, if I change the amount of blue, I get a different mixture. Change the amount of red, I get a different mixture. I encourage you to come and play with this simulation that I found for you. And of course, when you mix all three of them together, mixing light, by the way, we're not mixing paints, we're mixing light. Think 3 light bulbs. I can get, I'm going to try to get them all about 105-ish. That's close enough. All about 105-ish, and you get gray. Gray is just white that's not as bright in the middle here. And this is how TVs, computer screens create just a variety of different colors. And now we're going to talk about the subtractive color theory. What is this about? Well, this is very different. So this is when light strikes an object, some wavelengths of light reflect, which means they bounce off the object. Other wavelengths are absorbed by the object. The color you see when you look at an object depends on the wavelengths that are reflected. So let's scroll down here. Okay, if you have white light and it hits maybe a cyan piece of paper, the reason you're seeing cyan is that green and blue are reflected and the red was absorbed, and so on here. If you're hitting a magenta, someone's wearing a magenta shirt and white light like sunlight is shining on it, well look, the red light is reflected, the blue light is reflected, but the green is absorbed. And similarly here for yellow, where it's only red and green that are reflected from the white light and blue is absorbed. So this is how you can create a variety of different pigments, paints, colors for your clothing, uh, colors for your car, colors in a book, in a magazine. It's all about mixing pigments and paints. So that's what I just said here. Some colors are reflected, some are absorbed. And the colors you see when you look at the object depends on the wavelength that are reflected. For example, a red rose reflects red wavelengths of light and absorbs all the other colors. According to the subtractive color theory of light, color matter selectively absorbs different colors or wavelengths of light. The colors that are absorbed are subtracted. See, this is why it's called subtracted color theory, because the color that is absorbed is subtracted. You don't see it when it goes into your eye. A black object absorbs all colors, whereas a white object reflects all colors. A blue object reflects blue and absorbs all the other. That's how this is subtractive. The primary and subtractive colors of light for the subtractive color theory are opposite to the colors for the additive theory. Cyan, magenta, and yellow are the primary subtractive colors, while red, green, and blue are the secondary subtractive colors. Now look how I put this in red. This is really important. It is important to remember that subtractive theory of light applies to pigments and colors that they absorb. This is not like the one we did before, additive color theory, when we were using light bulbs and shining light, or a monitor or a TV with shining light. So a pigment is a powder used to color substances. If a color is absorbed, it will not make it to your eye. You will only see the reflected colors. Paint and pigment manufacturers mix all three of the primary subtractive colors in varying degrees to make any range of colors reflect from a surface. The printing press that produced the book uses the primary subtractive colors to create all of the pictures you see in a book. So, if you ever look at a color printer, it's got black ink, it's got yellow ink, it's got cyan ink, and it's got magenta ink. That's how we mix different colors together to make magazines and books and the rest of it. So let's take a look at a simulation. It'll be fun. So here is a simulation. So pretending you have yellow paint, yellow pigment, yellow ink, magenta ink, pigment, paint, dye, whatever word you want to use, and cyan, dye, pigment, paint, ink, what have you. This is what people will mix together to make the vibrant colors of a photograph in a magazine. And as you mix them, you see that the secondary color produced here is green. The secondary color produced here is blue. The secondary color here is red. And if you mix them all together, you get black. There's all of the colors are absorbed there. Actually, the computer printer, if it's out of black ink, can mix all the other three to make black. And once again, you can make a variety of different colors by mixing up how much pigment you put in there. Look at the middle there. You can get a variety of different colors, including gray. If I put all the numbers relatively close to each other, yeah, there you go, gray. So this is not additive color theory. This is subtractive color theory. This is how all the wonderful colors you have in a t-shirt, a dress, what have you, magazine, cars, the rest of it. Subtractive color theory. Okay, so back at our note today, uh, make sure you watch that video I told you. If you need to go over this video lesson, please do. Play around with the simulations. The links are there. Read your textbook. Answer the questions that I gave you for homework. The answers are already there, so you can compare your work to my solutions. This is 2 days worth of work. It's a very important topic, additive and color subtractive theory. If you have any questions, of course, there is a discussion group you can ask questions in. So thank you very much. Have a great day. We'll see you. Bye-bye.